Next, we want to talk about linear operators. So, an operator is a function from one vector space to another. It's just a function the way we all know functions. We call it an operator or a transformation simply when the function's domain and range are vector spaces. We just have a special name for it when we're talking about going from a vector space to a vector space. An operator is called linear when it can be distributed across addition and when scalars can be pulled out in front of the operator. That is when f of x plus z equals f of x plus f of z, and when f of alpha x equals alpha times f of x. So one of the most common examples of a linear operator is matrix multiplication. You can think of any m by n matrix as a linear operator whose domain is Rn and the range is Rm. Matrix multiplication is a function that operates on a vector from Rn and returns a vector in Rm. This is a perfect example of a vector space operator. And also, by the basic properties of matrix multiplication, we know that this operator is going to be linear. A times x plus z is a times x plus a times z. Also, a times alpha x is the same thing as alpha times ax. Of more importance to us in this class, the derivative is also a linear operator. So here we have a linear operator L, which is the same thing as the derivative. This linear operator acts on the function space C1, and its range is the function space C. So we consider the act of differentiation itself a function, which takes in differentiable functions as inputs and outputs continuous functions. So here we see an example of a differential operator acting on the function 2 sine of x minus 3 e to the x. So the input to this function is the function 2 sine of x minus 3 e to the x, and it outputs the function 2 cosine of x minus 3 e to the x. And we can see that this is in fact linear because we know that differentiation is a linear operation. In general, differentiation up to any order is a linear operator which acts on ck and outputs a function that is continuous. Next, we want to talk about linear operator equations. We can use a linear operator to obtain a linear operator equation. And this is an equation, f of x equals b, where f is a linear operator, x is some unknown vector, and b is a given known vector. As with most equations, the goal of this is to determine that unknown vector x. The classic example is a matrix equation, ax equals b. You saw this many, many times in your linear algebra class. Recall, this represents a linear system of equations where the unknowns are stored in the vector x, and the right-hand side of those equations is given by the vector b. If we assume that A is an n by m matrix, the domain for this operator, that is the space of all possible solutions to this equation, is Rm, while the range, the space of all possible outputs, is Rn. So outputs for this linear operator equation represented by b. Therefore, all possible b vectors are going to live in Rn. Now again, this is not the most important one for this class. We're going to be doing much more work with linear operators that are differential operators that represent derivatives. So let's consider the steady state heat flow problem that we discussed in the previous chapter. We can rewrite this problem as a linear operator equation by defining the linear operator LD. This operator has a domain C2D. Remember, this is the space of all twice continuously differentiable functions that already satisfy homogeneous Dirichlet boundary conditions, and it has a range of all continuous functions. The operator is defined such that it is negative kappa times the second derivative of u. So LD takes a function and returns negative kappa times the second derivative of that function with respect to x. Now that we've defined this linear operator acting on the space of functions that already satisfy homogeneous Dirichlet boundary conditions, we can rewrite the heat flow problem as the question, find a function u inside of C2D such that LD acting on u is equal to f for some continuous function f. Note that f has to be continuous so that it is inside of the range of the linear operator, so that it is one of the possible outputs for the linear operator LD.